Hey, welcome guys. Yeah, so before we talk about the character table, let's talk about some simple topic. Basically is the finite abelian group representation. Yeah, so basically, we spend like the 2 hours developing finite group representation theory, like talking about row orthogonality, column orthogonality, and we also proved that the number of the irreducible representation is the same as the number of the conjugate C class. Okay, so let me just write down finite list some important property in the finite group representation. Okay, so the important idea is that all reducible, all the representation is the direct sum reducible, and also first one we have the column orthogonality. Remember the inner products definition is basically let's say psi and phi is defined to be 1 over g and psi of g and the phi of g and these. Okay, and also we have the column orthogonality, which if you pick all the chi to be all the irreducible representation, and the g and h, and this guy will become what? G modulo CG. Okay, so G modulo CG, G divided by CG if they are the same conjugate class, else is they are 0. Okay. Third is the number of the irreducible representation. Irreducible rep is the same as the number of conjugate C class. Okay, the fourth is that the sum of the all irreducible representation dimension I belongs to G hat. G hat is the set of irreducible representation, which is the same as the group element G. Okay, so this is all the 4 important properties that we spend like 2 hours to prove all of it. Okay, so now we use this and some finite called finite abelian group. So actually this topic is simple, so actually we don't need all 4 of them. Okay, so let me prove a theorem. This theorem is very important, so you should remember. So if G is abelian, and I focusing on finite abelian, if and only if every irreducible rep, every E rep of G is one dimensional. Okay, there are 2 proofs, 2 kind of proofs. So let's just okay, so let's prove it by the so let's prove these directions. Okay, so these directions is much people usually talk about these directions. Is that if G is finite abelian, then every E rep is one dimensional. Okay, so the proof, the standard proof is that you know that your row of G will be finite order, right? So which tell you that row of G is diagonalizable for each G. But you know that row of H is the same as row of H, row of G, right? Which tell you that they are commutes, right? So actually, row of G and the row of H can be simultaneously diagonalizable, right? So it can be both diagonalizable, right? But this is commute with, but this any 2 group element are commute with self. So which tell you that there exists a basis, right, in the vector space V, such that everything is diagonalizable. So row of G looks like this, right? And every G looks like this, right? So it's diagonalizable. So that means each irreducible representation is just one dimensional. So one dimension. Because everything is diagonal matrix now. Okay. Okay, so this is one proof. Okay, let's prove the second. So the second proof, which is much more powerful, can prove both directions. So remember in the third property that the number of the irreducible rep is the same as the number of conjugate C class. Okay, so if G is abelian, that means the number of conjugacy class is just the number of the group, right? So that means we have all the number of the group. But the problem is that we have the number for property such that the sum over all the irreducible representation dimension square should be the same as whole group, right? But you have G of them, right? And the sum of square need to be G. So the only possibility is that dimension of VI is 1 for each irreducible representation, right? And so let me just say again. So number of conjugacy class, since it's abelian, so number of conjugacy class is the number of G. It's an order of G, but so that means the G hat is the same order of G, which means that you get some positive integer square need to be sum over G, but there are G of them, right? So the only possibility is that each one is 1. So for each irrep. So which proves that if G is abelian, then which is 1, okay? Each irreducible representation is 1. Conversely, if every representation, right, if every irreducible representation has dimension 1, which means what? Which means that the number of the conjugacy class will be the same as number of G, right? Because you will have G of them, right? But so that means every conjugacy class is in itself, right? So every order, every G, the conjugacy class of G is G itself. So which means that HG, H inverse will be the same as G, which makes that HG is GH for every GH, right? So that means G is abelian. Okay, so you might think that in our proof we don't use maybe in the first proof we don't need a finiteness, right? Because even though if G is not finite, then this guy probably the problem is that you may still need this. Okay, so it's not clearly that if you change the finite to be infinite, it's not clearly that every irreducible G is one dimensional. But actually, this is true. So the fact is that if G is abelian, then every irreducible G is still one dimensional. But conversely, I'm not sure. So I need to check the literature. But in the finite group case, that we have used these 3 or 4 properties, which we prove. Okay, so now the problem is that construction. Okay, so my goal is to construct all the finite abelian group. So my goal is to find all the irrep of finite abelian group. Okay, so the problem is simple, right? Because we can only working for let's say we only focus on the first step. We will focus on the cyclic group. So let's work on Zn, right? So my Zn is 0, 1, 2, -1, as I use addition as the group operations. So let's say, I know that row of 0 must be mapped to the identity matrix, right? But now it's one dimensional, so it's 1, right? How about row of 1? So once you fix the row of 1, then everything is fixed because let's say a row of 1 is x, then row of n, a row of m will be xm, right? So, but the problem is that your row of n need to be 1. So which tells you that your xn is 1. So x is the roots of n roots of unity, right? So it's exponential 2 pi I divided by n k divided by n, k is 0, 1, 2, -1, right? So there are n of them. But we already proved that you should have n irreducible representation, right? So which tell you that each k exactly 1-to-1 corresponding to the irreducible representation. Okay, so what I'm just saying is that the irrep of the Zn is just as a set, one can write as row of 1 from exponential 2 pi I k divided by n, so k from 0 to 1 to n minus 1. Okay, so if you are crazy enough, then you will see the irreducible of Zn is exactly Zn itself. So this guy is also isomorphic to Zn. So which makes that Zn hat is isomorphic to Zn. It's isomorphic to Zn, right? Okay, so yeah, so this is the which is a crazy part. Okay, but so now the question is that how about a general abelian group? How about finite abelian group? This is also simple because finite abelian group is we know that is the direct sum of cyclic group. That means that you can write your G as let's say Zn1 direct sum Zn2 direct sum Zn3 up to Z maybe Zn(k), and then you can take the heads, maybe become head. Okay, so actually there's a generator here that says tau 1, tau 2, tau 3 up to tau n, and so your case is just you just map the tau. You have also row 1, row 2, row 3, which is row right? So your row is specified by all of these row 1 up to row n, and then you specify. So there are n1 choice for row, right, and n2 choice for row 2, n3 choice for row 3, and nn choice for row n, right? And the product and total of all of them is the order of G. Okay, right? So which once you specify each row 1 the generator and the combine all of the combine is called row. Okay, so maybe this is the answer. Maybe we don't understand. Maybe we talk something simple. Okay, so the first the simplest abelian group, which is non-cyclic, is basically the Klein group, right? So it's Z2, Z2, and one can write as AB. Let's write AB. Let's see how I should write it. So I can write as let's see. So there are two generators, right? So one is A, one is B, right? So and one is A, one is B. So this group can be just written as the AB, and such that A squared is B squared is 1, and AB equals to BA. So this is one representation, or another is that you just write down every element. So you can write as a tuples, right? You have a 0, 0, 0, 1, 1, 0, 1, 1. And then these are the generator of these Z2, these are generator of these Z2, and then these are just sum of these, right? So all the four we have four irreducible representation, right? One is called trivial. So there's a trivial one, which map 0, 1 to 1, and the row 1, 0 to 1, right? And this is the first representation that's called row 1. And the second representation can map the 0, 1 to 1, and the row 1, 1, 0 to the two roots of unity, which is -1. Okay. And the third one is basically, let's say 2, 2, 2. Okay, so third one is mapped 0, 1 to -1, and 1, 0 to 1, right? And the first one is 0, 1 to -1, and 1, 0 to -1, right? So exactly there are four of them, right? And you can just easily say that in general, this is a general story, right? So for example, if you have Z2 times Z3, and then all the irreducible representation just map, let's say you can map row 1, 0 to exponential to plus or -1, and then map 0, 1 to 1 exponential 2 pi I divided by 3, and exponential 2 pi I divided by exponential 4 pi divided by 3, and then so there are 2 of them, 3 of them, so total you have 6 choice. Okay, so this is just all the 6 irreducible representation of the Z2 times Z3. Okay, so actually this solve all the problems of basically this given all the complete description of finite abelian group representation. But let me mention an interesting thing which you might notice, is that in the finite abelian group, right, we have already seen that G hat is isomorphic to G. So which means that in this case that G hat is also a group. But what is the group operations? So what is the group operations? So remember that the G hat is the set of irreducible representation, right? So you have 2 vector space, and then you can do the standard term is a direct sum of the tensor products, right? But the problem is that if you do the direct sum, the dimension become 2 because each one is a 1 dimension. So which is not inside this G hat. So the only possibility is that these guys should work in the tensor product. Okay, so theory is that every 1-dimensional irreducible representation at the tensor products should form a group, right? This is very non-trivial results, right? So actually, G hat is a group working in a tensor product. Okay, and then there is a theorem. I will not prove in this series, but maybe in the future there is a thing called pontryagin duality. I think it's hopefully I can spell it correct. This is called pontryagin duality, which means that if you take G is abelian group, it should be any abelian group. So for example, G can be taken as integer or a circle. These two are or real number. These two are like dual to each other. Okay, if you take the hat and you take the hat again, this will isomorphic to G. Exactly, whatever abelian group is. So for example, if you know that for analysis, you can view the irreducible representation of integer, right? Just the S1. And the S1, the irreducible representation of S1, basically is just a so-called Whiting number, so it's specified integer. So, and the real number, the irreducible representation of real number can be anything, right? So you can prove that it's just a real number itself. And so you can see that this pontryagin duality works for abelian group for these 3 cases, and also for the finite abelian group. Yeah, and this is the abstract version of Fourier analysis. If you're working in the pontryagin duality for real numbers, then you get a standard Fourier transform. If you're working in the integer and the circle duality, then you're working in a so-called Fourier series. So yeah, so this is the somehow the much difficult structure that I will maybe talk in the future video list, but not in this one. Okay, so next video we start to build some character table for the non-abelian group, and also for in this case that irreducible since it's 1 dimension, right? So character is actually the row itself. Yeah, so nothing special. So abelian case is simple. We don't need a lot of theory, but for non-abelian one, we will see you guys next videos. Subscribe to my channel. Okay.